Okay, so in this video I'll be covering the material as they're listed here. Okay, so if we wanted to solve for the current I/O by using source transformation, there's a lot of redrawing here, so I'll just kind of walk you through what I already have drawn on the screen. So first of all, we have current source in parallel with a resistance, so we can do source transformation. Alright, same thing over here, okay, which would give us this. And just real quick, note where I put the voltage source for the source transformation of this, because I don't put the new voltage source over here, you know. I want to put the voltage source in series with the resistance, so I'm going to put this source over here, not over here. Okay. So at this point now, we can combine these two voltage sources that are in series to get 24 volts. Same goes for the resistance to get 6 kilo ohms. Now at this point, I see that if we do a source transformation here, we can then simplify some sources even more. So once you do that here, you get this. So then you can see that the 6K and 12K are in parallel. Same for these two current sources over here. These two are in parallel. So you can add those up to get 6 milliamps. Right. So if we do a source transformation again, we can just get a single loop, single mesh circuit and solve for I/O as we've done here. Okay. So then I/O is just going to be 24 minus 12 over 8K to get the current. Okay, so in this next problem, they want us to solve for the maximum power transfer of some kind of load. So we need to solve for RL and then find the power of RL. And there's a three-step process which I've shown over here. Okay, so first we need to find VT to get the Thevenin circuit. So here's what I've done on the bottom here. So we open circuit the load and we solve for VT. Now I'm going to choose to use Nodal Analysis here because I can. So let's do green for this. So if I say that current's going this way over here and down over here, and this is kind of given to us as going down in the middle. This is some node Vx. Okay. Basically, we're going to use this voltage Vx, and then use voltage division to solve for the voltage over here. Okay. So here we go. Let's set it up. Okay, so this current over on the left is going to be 12 minus Vx over 3K is equal to the 2 milliamps plus Vx minus 0 over 4K plus 2K. If this were our ground node on the bottom here. Alright, so you can solve for Vx and you get 4 volts. Alright. So because in this closed path right here we have a known voltage being across the current source, and that voltage is just Vx, and all series resistors in this closed path, we can use a voltage divider. Okay. So Vt is going to be equal to Vx times 2K over 4K plus 2K. So Vt is then going to be 4/3 volts. Okay, so we have Vt, and now we need RT. And so because we're solving for RT or R Thevenin here, you know, in this circuit I see a voltage source, so I'm going to short this out. I see a current source, so I'm going to open circuit this. Okay, so we have the voltage source being shorted out. We have this current source being open circuited. We have the 4K and 2K resistors. Here's RT, the terminals of RT. 4K, 3K, 2K. Okay, well these two resistors are in series, and that will be in parallel with the 2K. So RT is going to be equal to 3K in parallel with 4K. Plus 2K, or just 14 over 9 kilo ohms. So 14 over 9 kilo ohms is RT. And so with that, now we can draw the Thevenin equivalent circuit to look like this. Alright, and now so to find maximum power transfer, we have to set RL to be equal to R Thevenin, or just RT, which is 14/9 kiloohms. Alright, so the power is going to be just, V squared over R, or just I squared R. So this is going to be equal to 2/7 milliwatts. Okay, so in this next problem here, they ask us about an inductor, and here's all the important stuff. Here we go. So just note that VL is equal to L times the time derivative of the inductor current, right? Well, a derivative is basically just, the change of one thing over the change of the other thing, right? So we can solve for L, so L is going to be equal to just VL times delta T over delta I. So all we do is we just plug and chug and we get L is equal to 2 henries.